Just unmute and you can talk to me.
Yes, sir.
Yes, sir.
Yeah. So what we have today example is, we have an example of flow mix and heat transfer. What we have is flow mix and heat transfer. What do you meaning of this flow mix? There is a cold water and hot water which is mixing in a one pipe. So in that pipe, when two, the hot and cold water, hot and cold water was mixing, in that portion, how the heat changing is happen, what is the outlet velocity, what is the outlet temperature. So that things we are going to predict in this analysis. Now first, I have a pipe section. First we'll see the, the problem description. What we have, a problem which consists of a cold fluid which is at a temperature of 293.15 Kelvin, flows into a pipe through a large inlet and mixes with warm fluid at a temperature of 313.15. So warm water, in the sense you can also consider that hot water which is a temperature of 313.15 Kelvin, that enters through a small inlet located at the elbow. So this portion is a small inlet, you can consider this. The mixing elbow configuration is anchored in a piping systems in a power plant. The application is in terms of power plants and also in the process industries. Okay, so this type of same application was which is used in power plants and also in the process industries, and it is often to predict the flow field and the temperature field in the area of mixing region in order to properly design the junction, in order to properly design the junction that we can we are going to find it. It is often too important to predict the flow field and the temperature field in the area of mixing region that we have to decide. So first you can observe it, the inputs over here they have given the velocity is of the cold water which is having, this is a large inlet, this is a small inlet, and this is your outlet. So here we have the large inlet now which is having the fluid is traveling with 0.4 meter per second, and the temperature which is having 20 degrees, and I is equal to turbulent intensity I equal to 5%. And here in the small inlet which is having 1.2 meter per second, and the temperature is 40 Kelvin. But here how much, when you convert into degrees, like 313.15 Kelvin, so it has been converted 20 degrees plus 273.5, it will be converted into Kelvin. So 40 plus 273.15, it will be converted as a Kelvin. No sir, I want to subtract, then 273 minus 273.15 minus 40, then you will get the temperature. Okay, so they have given the parameters of a liquid. So they have given density, viscosity, conductivity, thermal conductivity, and specific heat. They have given the parameters. Using these parameters, I am going to solve the problem. And the diagram, so using this diagram we can design the model. Okay, so first I'm going to use it. So go with the workbench. Here we can go with the workbench. You can start the workbench. I'm using workbench. So try to give okay. So in that, what I'm going to do is I'm going to take fluid flow fluent. Just double click on this. In order to start the fluent, I'm going to use fluid flow. I'm going to take fluent. So what is the project name? I'm going to take flow mix and heat transfer is my example. I'm going to take it here. Okay, this is my example, flow mix and heat transfer. This is my example. Now what you're going to do is, in that I'm going to create a geometry. If you have already a geometry, then you can draw it, or you can import it. No sir, I don't have geometry. Then what you do is you can create a geometry, or you can save it this. So in the desktop, I'm going to save it in the Fluent. So future reference, I'm just saving it. Flow mix and heat transfer. I'm going to save it this. Okay. Yes. Now go to the geometry. So out of these three standard planes, I'm going to take XY plane. Just go with look at. So here we have primitives, no? The people who knows Ansys, they were aware of this primitives. So out of this, I'll go to first. I'll change this. What are the units it is having? I'm going to check it there. So 25 mm dia, and all are in terms of mm. I'm going to change the units to into millimeters. Okay. Just again fit it. So create primitives. You can go with the torus shape. Okay, so here we have now it is exactly in the center. No, this is our center point. Now in the diagram you can consider there is a there is a one plus symbol which is indicating that you can consider center. So this is your circle section. Now from here to here, if you measure, you can measure it. Now from here to here, so what is a dia from here to here? That is of 100 mm. That is inner circle dia is 100 mm. 100 plus 100. If you take this whole circle, it will be from here to here, it will be 100. Now there is 100. That is external circle is 200. 100 plus 200. I mean 100 plus 100. 200 we have. So that I am going to use it here. So inner dia is 100 units. Outer dia is 200. I am going to take it here. Right. So along how much degrees? I want to rotate off 90 degrees. Only 90 degrees I want to have. Right. Now it was showing in the positive direction of y, positive direction in the y, it was showing that, but I don't want to have. Then you can change it to negative direction, -1. I'm going to use it to the other side, right? So that we created and try to generate it. We have this section, right? Now again, what is the length of this? So from here to here, the length is 200 mm and top is also 200 mm. That I'm going to do extrude. So here you can take it this length. So direction, I'm using this is the direction. So go with opposite direction, that to 200 in the depth and generate here, and this portion also. You can select this and you can define the direction. I'm selecting this, try to generate it. Okay, so inlet and outlet we drawn, and there is a small inlet which is having so from here the center is 137.5 which is having, so I'm going to use it that. Sir, how we do? So out of this, I'm going to take this ZX plane. Just go with look at. So create a circle. Exactly how you're going to draw it, I'm going to draw with respect to this center. I'm going to draw it here. Exactly horizontal way. I'm just using this. So here we required. Then what you can do is, then you can mention this dia which is having of 25 mm. The dia. And the length dimensions with respect to this and with respect to the center point which is having how much it was, which is having 137.5 and 225. So you can take it 137.5. okay, this is, and you can go with extrude length, apply, that is of 225, and you can go with your reverse direction, you can use it here. Okay, so this is a small inlet, you can construct this. Now now this is a pipe section. Yesterday we were talking that exactly where will be the maximum flow. I was talking yesterday also, I was saying you this concept. Suppose you have a pipe section like this. Now where will be the maximum flow? The maximum flow will be there exactly at the center. At this center location will have maximum flow, we can construct this. Okay, the maximum flow will be there exactly in the center. So why sir, why it not be there in the walls? Because due to viscosity, the fold will be opposing. So what I do is, out of this I'm going to take only this portion, only the half portion I'm going to take it here. So only the half portion I'm going to take it, so that only this portion I'm going to take it, so that this will be center, right? So that's why what I do is I'm going to cut it this. So go for here, tools, symmetry. So with respect to exit plane, apply, I'm going to generate it, right? Now this is your middle portion. Are you clear with this? 5 of you.
Yes. Yeah.
And one more person joined. Okay,
Yes,
6
sir.
of you. So that is exactly the center, right? Now what I do is again go for here the solid object. So change type to fluid. I'm going to change it here. Here you can change type to fluid. I'm going to change it here, right? This is the foremost thing you have to do it, right? Once you're done, try to close it here. And again you can save this project. Yes, we had to be saved. Go to the mesh. It will take 1 or 2 minutes to load the file. If you have good graphics, within minutes it is going to complete. Okay, so we have that file. Now you can just cross check it, just put it here in this way. This way I'm going to use it here. Now before we do the meshing, so what I do is I'll go in creating the neighborhood selections to this. So this faces, we can take this as you can right click here, create a neighborhood selections. I'm going to use this as velocity. Instead of velocity you can go with what you can do is I'm going to take this as inlet large. For my identification I'm just giving this. You can give any name for your identification. Okay, just inlet large, and this is you can take with right click, you can go with create neighborhood selections. I'm going to get small inlet, you can give it here small inlet. I'm going to use it this. This is your outlet portion. Create a neighborhood selections, outlet, you can go with that. Okay, and next case is, now this is your symmetry, this is exactly in the center. We want to calculate our temperature, so you can define this as a create a neighborhood selections. So what you can do is you can go with this symmetry as a name. Okay? So that I'm going to use it. So these are the neighborhood selections which we gain. So if I get, as we know that, as we know, if I do general mesh, results will be appropriate. Now what you do is, at this walls region I want to have fine mesh, and in the middle I want to have general mesh we can do. So what I do is right click here, then you can go with here, you can expand this sizing. Okay, I'm going to use it, the relevant center we can go with here, center exactly I'll be going with fine. I'm going to use it here. So units, what units it has been having in terms of meters. Okay, so fine, I'm going to use it here. And smoothing option, this is medium, no, I'll go with 5. I'm going to use it here. And this is, we gave it, right, relevant center to fine, no. And the next case is I'm going with body sizing. Now right click here, you can go with here sizing and change type to body. You can select the whole body, apply. So what sizing you are giving? So I'll go for 6 e power minus 3. I'm going to use it this. Okay, so I'm going to give this sizing. Now once we have given this sizing, and one more important thing you have to do is, so you can go with mesh, no, you can go with here in the mesh type. So in the inflation type, you can go with it here. Expand this inflation. In that inflation, you can go with here. Yeah. So inflation use output, you can go with programming control. Okay, I'm going to go with programming control of 5 layers. It is going to be generated that. All right. So once we done it, so try to generate the mesh with the whatever settings you give. It is going to be generate the mesh. Now you see exactly this region we got it fine, and rest of the things are with the default mesh you have. Are you able to observe this?
Yes, sir.
6 of you, is that clear?
Yes, sir.
I need answer from other people also.
Sir, once
Hello,
more.
hello, sir.
Yes, sir.
Yes, yes.
Hello, sir.
Yeah, please.
Sir, yeah, this is Santosh. Sir, in inflation, you selected 5 layer, okay?
Okay.
In yeah. So we need to define some boundary or something there from which surface or which boundary we that
No,
five
no, no.
layers are.
See, thing is that now I went for total body I've selected. No, when I give body sizing, total body from this layer it is being given. No, sir, in the particular phase you want to give inflation, then you have to select. Here it was when I go for here. No, inflation type. So it is
So
taking a
when we
programming
select
control.
when we select body, then it adds layer from boundary surfaces, correct?
Yes,
Outside
yes.
surface.
No, if you want to have from particular surface, what you do is right click here, inflation. You can go with the particular surface. You can give it here.
Yes, yes. Yeah.
Okay, that way
That
you can do it. So
okay.
now what I
And
did is,
body
yeah, yeah,
by
please.
default from outer surface it adds 5 layers. Correct.
Yes, yes, yes. There is also one more question. Can you repeat the mesh part? Yes. So what I did is, if you go with the default mesh, I hope you won't get better results, right? Now what I did is in the mesh, so I went for, I think you were aware of this. So if you use for sizing, you can go with fine mesh, fine and smoothing. You will have high quality elements. You will be generating this fine, and here also, you will have fine, coarse, fine, and medium. You will be having. So this concept will teach usually in Ansys workbench. Fine, coarse, medium. You will have all this stuff. Okay, so I'm not going to touch this. Now here also I'm going to use smoothing because I required fine elements, because I'm using very precision element contact, so that I want to have precision smoothing we require. Now the next case is I'm using inflation. What do you meaning of this inflation? So inflation in the sense I want to create a layer by layer, so that in order to get better values I'm using here. You can see the layers how it was there, the layers. No sir, I don't want to have layers. Then you can try to avoid it. Instead of program control, you can put it to none. You can use it that, right? No sir, on the particular phase you already gave the name or selection, right? Already you gave a name or selections. So how many you have? 1 2 3. No, on the particular phase you want to give, then you can go with all phases in the name or selections. You can go with here. Now, whatever the phases you have, you can define this. Okay, so here you can go with again inflations. So select the name or selection. It was asking. Now when you click it here, you can select on the particular phases. No sir, I don't want to have all body you want to use. Again you can go program control, try to generate again. So once it has been done, just try to fit to the screen, right? So again, now sometimes, usually not in other systems, in my system it is getting collapse, might not be there in your system. If you are using updated version, it will not there, because I have licensed versions. So that's the reason every time it is showing in this way. So what I do is I'll export this mesh file, export it. So you can go with here in the Fluent. So what you do is I'm saving this. Instead of this, I'll save this as a flow mix. I'm saving this. So in terms of mesh file, it is going to save it. For future reference, I'm saving it. Okay, so this we have done. Again, you can save the project. Yeah. So now it is asking for update. No, it is asking for update. If it is getting update, it's fine. Otherwise, we have to import the mesh file again. So try to update it. Now you see it has got unable to update the model. So what could be the reason? No, you can show the results. You can go with here. See, installed Microsoft, error, update failed, mesh component, unable to update the model. So what I do is, you can just clear generated data. The same file already we saved the mesh file, no? So what you can do is you can remove this. Go with again fluid flow fluent. So from this flow mix and heat transfer. Okay, so you can try to import the mesh file. Already we saved it, right? Browse it. So here we have, right, which was saved. Now just try to import it. It will not happen in your system, I hope, right? So you can know once you done it, now it will open in the Fluent application, right? Double click on this setup, it will open in the Fluent. Now here, what do you meaning of this? When you start the Fluent directly, if you double click on this setup, it will open the Fluent. No sir, if you have already mesh file, because I saved right now, right? So you want to directly, you want to start the Fluent applications, Ansys, you can have the Fluent application directly. You can start it from here. You can directly open the Fluent application. Anyway, it's fine. Either you want to, if you have mesh file directly, you can put it here, or already we have, no, just click it on here. Automatically the Fluent will be opened here. Anyway, it's fine. So now what do you mean? Automatically my system is taking, that is a 3D object, 3-dimensional, it is taking that. Now again, double precision. What do you meaning of double precision? So double precision is like for every minute node, it is going to calculate the results. Minute node or minute element, it is going to calculate the results. Okay, so what happens if you are not checking this? Result will be solving that, but it is not like 5 to 10% changing in the results, right? So I'm using this. Now display mesh after reading. No, mesh should be displayed once you give OK. It is going to display the mesh. Enable the graphic window, workbench color, whatever the color of the workbench you have, the same color will be in the Fluent application. No, you don't want to show the application, you can do. So when you expand this, so where the software has been saved, all this, it is going to be shown here, right? So next case is, what do you, yeah, please.
Okay, no.
Okay,
No questions.
so okay then, so what do you meaning of this processing options? So series or parallel you have, what do you meaning of this? Suppose in your companies you have to run 2 or 3 problems at a time. In your companies you want to run 2 programs or 2 files you want to run at a time, so you can use for parallel. So how much memory you want to allocate it for one problem, how much memory you want to allocate for other problem? Because in my laptop I have only 8 GB of RAM. Now suppose you have more graphics and more RAM, some of the memory you have to allocate for one problem, some memory you want to allocate from, so both problems you can run parallelly. If you have that much graphics in your in your system or in your laptop, then you can allocate some memory for one problem, some allocate some memory for one problem, you can go with that. No sir, I don't want to have that, so I will calculate one problem, so then you can go with series. Okay, so when I go with parallel, then you have to allocate the memory, what is a processor, what is the GPU of machine size, you have to allocate it that, right? Now I'm not going to use that, I'll go for series. So once you done it this, so just go with OK. Now it is going to read the mesh file. So the Fluent application, now this is your Fluent application. Okay, just try to put it here and make this part fit to the screen. Now the first thing is, here we have this total graphics, and this is your command, whatever you want to give any sort of command. In the coming sessions we also give the commands also that we discussed. Command prompt we can give it, just give it enter, so that you can give a command. You can see like any command you want to give, you can give it the command over there. So here we have the total, whatever we have in the left hand side. I mean, in the left hand side, you have general. You can just put it here. How many windows you have, we can use. Already we have any file, you can try to import this. Okay, profile, no, or file. You can just go with save project, lead or the setup, synchronize or read what you want to read, or read the mesh file you want to read. You can read that. So import what sort of import I want to import the mesh file, data file, case file in the sense, even case file is a setup file, and data file, case or data file, abacus file you want to import. So there are different solid file you have, even nastan also you have, nastan, hypermesh also you have over here, right? So every file you can import, depends upon the solver, what solver, because dat file is .dat file is for hypermesh, you can take dat file, and even case and dat file you can import it. So how do I import, sir? Now when you go for dat, you can see the extension .dat file. So for example, I have a dat file of hypermesh, you can see here. So go with hypermesh, because already I've solved, I think Gokul knows that 3D. Here it's showing dat file, right? I think here we don't have 1D analysis. And put it all files. So .dat file will be there. Here it's showing, right? Output file, results file. Just go with that. So you can see .dat file. You can put it to dot file. So you have .dat file. You can import this. Right? You can import the dat file. Results file you can call .dat file is the results file. Right? So this way you can import it. So file and mesh. How you do the check polyhedral elements, merge elements, because already we did all this mesh types in your workbench. So checks defined, all you have, whatever the command you have here, the setup and all you will have in this menu options, everything you will have there in the menu, right? So again, the shortcut keys are there. Now you can just press middle mouse button to zoom in that area. Press middle mouse, keep on pressing. You can draw a box shape, you can use it. Now sir, I want to pan it. Just try to fit it again, fit to the screen. You want to pan it, you can pan it this. Okay, so you can use pan it this. When you right click, you can pan it. So zoom in, zoom out, you can use zoom in, zoom out. Okay, so this is like a kind of prop, you can use it. So you click on this prop, so what you want to know, you can see that wall ID it was showing, wall solid. You can just click it on the particular area, so that it will shows us here, right? Fit to the screen. I want to use rotate, you can use it here, right? So here we have total, setup, solution, results, and parameters, and customize you have it. So when you expand this setup, the first one is the general. In the general, the first option is scaling. What do you meaning of this scale? Because usually you won't draw your model in Workbench, or you won't draw in the Fluent. You will draw the model in other modeling software, and you will import that file to in the Fluent. For example, for instance, you drawn a model into inches. Suppose you drawn your model into inches. Now I want to scale that model in terms of millimeter. First you view the lens in terms of, now we already drawn this part in terms of millimeters. We drawn, you can see length, x length is 50, y length it was showing this 225 mm. So which was, we already know that we drawn in terms of mm. Now how you want to scale it? Now I want to scale in terms of inches. Then you can use for scale, right? So we know that we have drawn this part in terms of no sir, you drawn this part in terms of inches. Now I want to scale in terms of millimeter. Then you can scale it. No sir, I want to scale along in the x direction itself, along x direction. Then you can put it here. You can go with specify the scale factor along in the x direction you want to scale it. How much scaling you want to give, y direction you want to scale, z direction you want to scale, because it is a 3D object showing 3-dimensional. If you do a 2D object, only 2 dimension is going to represent that, right? No, I'll put it in terms of millimeter. You can use it this. So once we're done, I'm not going to scale it right now. Just try to cancel. Now go for checks. What do you meaning of this checks? Check is that any error, whatever the error we have, the total information it shows us here, x coordinate, y coordinate, z coordinate, what is the total information of this object it is going to show us here. Okay, and report the quality. Is there an element is getting failure like aspect ratio, Jacobian ratio, minimum length, maximum length, warpage. So anything is getting failure, it is going to include. Now you see auto skew ranges from 0 to 1 where the value of 1 is 1 close to 1 corresponding to low quality. Okay, so that it was showing this. Any warning message it shows us here. Then what we have to do? Again we have to remeasure the part again. You have a low quality elements, then again we have to generate with a good quality elements to get a better quality results. Now, once we done, then what type is this? Either it is a pressure based or density based. What do you meaning of this pressure based? Mostly your problems will be pressure based. Most of the cases, like 10 to 15% your problem will be density based. Then how could be the density based? So might be we studied in your strength of metals subject, not in strength of metals, uh, fluid mechanics. I think fluid mechanics we have a subject, right? Core subject for mechanical people. Convergent, divergent might be you have heard that norms. So you have this area. Suppose you have one pipe like this. So it is getting expand. Now from here to here it is compressing. No, the fluid is getting compressed now. If you see this area, the fluid is getting compressed. When it is passing, the fluid is getting compressed here. Now again it is get compressed here. When you compress, the pressure will be increased. So this way we have. Now again it is getting expand here. Now it is getting expand here. Changing in the cross sections, you can call this. It is getting expand here. Now here it is getting compressing. Now here this region is getting compressed and this region it is getting expand. So this type of problems we can call this as a density based problems. What you call? We can call this as a density based. Now our problem is not a density based. Now it is like just simple section we have. So from this portion from to here the same cross section we have here. From here to here we have the same cross section, inlet and outlet. What I do is I'll use pressure based and velocity formulation. It is absolute velocity. What do you mean by? We have constant velocity, there is no relative velocity. What do you meaning of velocity? Changing with respect to time the velocity, then you can go with the relative velocity. Changing with respect to time, so 2 seconds how much velocity, 3 seconds how much velocity, 5 seconds how much velocity. But here I have absolute velocity 2 meter per second, that's all. 2 meters per second it has been traveling, the whole the fluid is traveling with 2 meter per second, it has been traveling. But 1 meter per second, 2 meter 2 meter per second, the velocity again 3 meters per second, it is gradually changing in the velocity. That you can go with relative velocity. You have to change that. Now sir, it is constant velocity, you can put it to absolute velocity. Please respond. Are you clear with this what I'm teaching?
Yes, sir.
Yes, sir.
Okay. Now here we have, I think the people who are learned workbench, they have steady state thermal analysis, transient thermal analysis. What do you meaning of that? Steady state thermal analysis, we are comparing with respect to time. Okay. Transient thermal analysis, we are comparing with respect, steady state thermal analysis, we are not considering with respect to time. Transient thermal analysis, we are comparing with respect to time. Time will be a parameter. Steady state, we are not comparing with 2 seconds how much heat is been transferring, 3 seconds how much heat is been transferring, 4 seconds how much heat is been, we are comparing with respect to time. If you're not considering with respect to time, then you have to use steady state. Okay. Suppose if there is any gravity here, you can put it the gravity here. In the description, in the problem description, if they mention as a gravity which was acting in the direction, then definitely we have to assign the gravity. You want to change any sort of units, you can change the units. Suppose usually you see, suppose when I go with boundary conditions now, when I go with boundary conditions, how much velocity it has been traveling, you can click on this. When I go with large inlet, so how much it has been traveling, it was showing the units are in terms of millimeter per second, velocity is meter per second. Now sir, I want to change the units. What you do is go for here in the general, then you can change the units. So what length, we can change the velocity, v, velocity. So what it was showing, meter per second or feet per second. You can change the units. Like temperature, I want to change it here. So PQRST. You can change the temperature. What default it was Kelvin. No sir, I want to put it in terms of degrees. You can put it in terms of degrees. Right? So this way we have to change the units. Now if you are not okay, sometimes they will give in terms of Kelvin. Sometimes they will give temperature in terms of Kelvin, or the velocity they will give in terms of millimeter per second. They will give you this. Based upon that you want to change, then you can change the values over there. Okay, so that I'm going to use it. Now what I'm going to use it here, I'm going to change the length to mm. Sir, what, how sir, why we have to change? Because our dimensions, you see, our dimensions are in terms of mm, right? So what I do is go for units, length, no, you can go with your length, PQRLM, length in terms of mm. I'm going to use, already it is in terms of mm. Close it here, right? I'm going to use it that. So once we have this, then what you're going to do, so I'm going to use it. So now you see what important things we have to calculate: predict to flow field and also temperature field. Predict to flow field and temperature field. So whenever this, generally you were clear, I hope. The general tab you are clear. Now when you go with models, what sort of problem you want to solve? Either you want to solve laminar flow, either you want to solve what do you say, laminar turbulent flow, either you want to solve steady flow, unsteady flow, viscous flow, non-viscous flow, Newton flow, non-Newton flow, or temperature problems, or different types of problems you have. On what basis you want to solve this problem? So here this model will define. This is very much important, this model. There are n number of models we have to work out, but we are not that much proficient in that. But I'll be teaching whatever knowledge I have. I'm going to teach you in that. To be frank, I'm not that much proficient in all these cases, because even we have not worked on this acoustics, solidification of melting, decreated method. Some cases, almost 50 to 40, 50 to 60%, I was good at this. But lot of depth in this, lot of in-depth knowledge we is required for this. Even PhD persons also not aware of some of the tools. Okay, sir, I was good, I want to do some PhD in some sort of projects, then better to download some help files, then you can give. There are a lot of help files which Ansys is providing it. If you're using license versions, lot of help. Suppose I want to know about this acoustic, then you can do Control 1, so that you will give total information. Okay, so as per our data, as per the student knowledge what we required, you can teach them, because we are not making student be that much proficient in the Fluent. We are making what is Fluent, what you do in the Fluent, how to solve the problem. If he is that much proficient, definitely he will be getting good job in the things. So what you are doing, what you are teaching to the students, the thing is that you are making the student to join in some company. Then after you enter into the company, he can gain some more knowledge. The initial input you are giving to the students, and rest of the things he is going to learn once he enter into the company. So that's we are making them to trained. So that you have to understand. So first, go to the model. So here I'm not going to use multi phases. What do you mean by of multi phases? Suppose you have a fuel tank. There is a mixture of fuel and air. You take, you open the diesel tank or you open the petrol tank of your bike. You will have, it is a mixture of fuel and as well as air. So you want to go with multiple phase, then you have to do the analysis of that. Okay, now I'm not going to use multiple phase. We have this multi-phase problems also. I'm going to teach you in that, right? So first case is we have the energy. What do you meaning of energy? You remember, guys, whenever I'm talking about energy in the sense temperature. Energy in the sense temperature. Now you see what we required, temperature fields in the area of mixing region we want to calculate. Now what I do, definitely I have to activate this energy. I want to calculate this energy, that is temperature I want to calculate. Now what sort of problem it was? Even it is not a laminar flow, It is not a constant flow. It is a turbulent flow. So what I do is change type to turbulent flow. So in that, if you go for viscous, no, you see how many types we have: transient, K, omega, problem, transient, SST, 4 equations, Reynolds stress, scale additive simulation, detached eddy simulation, large eddy simulation. There are different. When I explain large decision, you have one more models. There are a lot of things we are there. Okay, as per the content I'm going to teach you. Okay, so now what I do is I'm going to use as per the problem what things we required. So I'm using K epsilon second equation. So what do you mean by second equation? K is one parameter, epsilon is one parameter. Using these two parameters, I'm going to calculate the temperature and also I'm going to calculate the outlet velocity. K epsilon second equation is my problem, so I'm going to use it that. Okay, so now K epsilon second equation. Now where you want to predict your temperature?
Sir, excuse me, sir.
Please.
Sir, we choose K epsilon 2, right? For this problem.
Yes. Second equation,
So,
yes.
yep. So, apart from that, we have so many flows, right? I think
Yes.
the apart from the laminar flow, all the flows which is related to turbulent flow.
Yes.
Yep. So why we are specially chooses K epsilon? So is there any recommendation to choose
It is
K
not
omega?
most of the flows are K second equations. Now omega is like 3 equation you have, omega and all constant values. There are theories behind this. If you want, I'll show you this PDF where are the theory calculations why we have to use this K epsilon.
So why can't I use the Reynolds stress or some other things for this particular problem?
Which one? Reynolds stresses.
Yes.
You will get the values, but it is not related to this problem. It is related with other problem. See, now if I want to use Pellard alarms equation, this is totally related to aerospace problems. So you want to calculate coefficient of lift, drag. Yes, air type of analysis you want to calculate, then you have to use. This is totally meant for that. Now, if I want to use Reynolds stresses, or if you want to go with radiation type of problems, totally you will calculate the how much radiation is getting from the heating object. Okay, so how the inside combustion is happening. So that all you want to get. Based upon that, we'll be using. Simply, we are not going to use it. Based upon that, we'll use it. Now, for these cases, I want to calculate the flow as well as the temperature at the mixing region. So that's the reason I'm going to calculate K epsilon second equations. Okay. So now next cases, I'm going to use in which region you want to calculate this area at the area of enhanced wall rating. Mostly I want to calculate at the walls regions how the flow will be there. I want to predict that. Even I want to calculate the outlet velocity also, that we can determine. So first I want to calculate enhanced wall treatment because over this wall region I want to predict, right? I'm going to define that. So I'm not going to disturb these values. I'm going to use the constant values, right? Once you define, try to give okay. This is the case, I'm going to use it, right? So once you define the next, you can go with material. Now as they already mentioned here, no, what they mentioned, the properties of the fluid they have mentioned: density, viscosity, conductivity, specific. So these parameters I'm going to use it here, right? So now here what we have only the fluid is air. Then sir, what about the liquid? How I have to add the water? Click out on the fluid, create or edit. So in that we can go with Fluent database. No, you can go with Fluent database. In the bottom, you can change it. No, this is a fluids. All these are fluids. You can see hydropyroil, or we can have different fluids. All these are different fluids. You can water vapor, water liquid. All this you have. Oh sir, I want to have solid metals. Then you can change type to solid materials. So aluminium as solid, copper, calcium carbonate, calcium oxide, calcium sulfide. You will have all this. No sir, I want to have fluid. So what you do is change to water liquid. So try to copy this. Okay, copy it, right? So once you copied it, again go for water liquid. Now create or edit. Now what you want to edit? So what is the density which is mentioned there? So density they have given as 1000 kg per meter cube, and specific heat, how much they have given? The specific heat they have given 4216 joule per kg Kelvin. So I'm going to use it that 4216 joule per kg Kelvin. thermal conductivity, how much they have given, I'm going to use it. Thermal conductivity, okay, so 0.677 watt per meter Kelvin, I'm going to use it. Okay, 0.677 watt per meter Kelvin. And viscosity, so this how much they have given, so that is 8 into e power 8 into 10 power of minus 4, that is I'll be changing that values 0.000, you can put it this like 8 into 10 power of minus 4, right? 1 2 3 4 digits, so I'm using this. Okay, so change or create and try to close it. We have the same property we have, right? I'm going to use it this, right? So we given now now you have given the you have added the metal. Now we are making to pass water to flow inside. Sir, how I have to define to make water to flow inside? That means you have to go with cell zone conditions. Go to the cell zone conditions, click on the solid, so go with edit. So in the edit, change type to water liquid, so that water is going to be passed inside, right? So try to give okay. So once we have defined this, so then what is the next case? The next case is I'm going to use water we have defined, right? Then we have to define. Now the other important is how much velocity it has been traveling. It is traveling with 0.4 meter per second, and T T is 20 temperature is 20 degree Kelvin. Turbulent intensity. What do you meaning of this turbulent intensity? I'm going to tell you. So inlet large, okay. So you can just double click out. That means this is your inlet large, right? Sir, can you show me that again? Yes. Now I'll show you this. Just rotate it. Go to the models. So here we have display type now. So you can just go with undo all this. Inlet large. This is your inlet large, and in small inlet. This is your small inlet, and outlet. The top one is the outlet. So the symmetry. This is your symmetry, and the total inside solid elements. You can go with this total solid elements, right? So once you done it this, then you can go with large inlet. So go with large inlet. So go with edit. Now it is automatically taking type. This is very important. When you click on the symmetry, no, it has to show symmetry. If it's showing with other type wall it was showing, that means your problem will go wrong. Definitely it has to show with the symmetry type itself. When it's showing inlet large, then it is take velocity. Now suppose if you go with inlet vent or inlet fan, that is going to change with other problem. So every time you have to check it this. Now don't change this, no. I'll go with velocity inlet, right? Velocity inlet, right? So how much it is, no? Just go with here, edit. So how much you are going to define this velocity inlet for that cases? Velocity inlet, I'm going to use it. So now we know the dia of this, so which is of 100 mm, right? 100 mm. So I'll go with normal to boundary, I'm going to use it. So I'll go with instead of components, because I know the direction, which is x direction. So that's the reason I'm using velocity, which is of 0.4 meter per second, which is along x direction. You can see x direction. So now here we doesn't know k value and epsilon value. We doesn't know intensity and length scale. We doesn't know intensity. We know intensity, but we doesn't know viscosity ratio. So we know the intensity and we know the hydraulic diameter. So this two input parameters I know. So what intensity is, they are given 5%. So what is meaning of hydraulic dia? Okay, so which is of 100 mm. 100 mm is the dia, right? So that I'm going to use it here. Right, sir, what do you meaning of this intensity? Yeah, please.
Yes. So hydraulic diameter is the size of the pipe, right?
Pipe.
Okay. So in turbulent intensity, what does it mean, sir?
That's
So
what
we
I'm
give it as 5%. Okay, fine.
yes. So now depends upon the the sections, depends upon the type of application, will be giving the intensity. I want to show you that. Yes, here we have this. So how you calculate the intensity, I'll be showing that. So if it is a large type of flows, we have this. So where you have I u dash by u. No, first I'll show you this, how you calculate this intensity. On what basis? Now first you observe where it is high turbulence cases, it will be vary between 5% to 10%. High turbulency cases. What do you mean by turbulency? The irregular movement of your particles. If you have a regular movement, that we call as turbulent, laminar. If it is like irregular movement, it is like irregular movement, that we call as turbulency. So which is the high turbulence cases, that you will vary with 5% to 20%. It is medium turbulence, will go with 1% to 5%. If it is lower turbulence cases, then we use 1%. Then what is your meaning of this turbulent, sir? So when you define I stands for turbulency, turbulent intensity, where U dash is the root mean square of turbulence velocity fluctuating or fluctuations, and U is the mean velocity, that is of depends upon the Reynolds number. How you define the Reynolds number? Any idea how you calculate the Reynolds number? What is the formula of Reynolds number? How you predict the Reynolds number formula? Anyone? How you define the Reynolds number based upon this Reynolds?
So if it is 2000, then we call
no,
it
we
as
know that, but I was talking about the formula. Okay, so Reynolds number, how you define this? RE is defined as, because we studied in our fluid mechanics. So RE is defined as rho V, this density of your dia, rho V velocity divided by and mu, coefficient of viscosity. So this we have, right? So from this you will get it here, the Reynolds value. Depends upon the Reynolds number defined. It is a laminar flow, turbulent flow we define. So from this, now turbulent kinetic energy is you can have this. So you will get it from this, the turbulent intensity, U dash and U value. Okay, U dash is the root mean square of turbulent velocity fluctuating, and U is the mean roots velocity. So if you want to take, it doesn't have any change, but usually we'll go with 5% to 20% max, we will go with that, right? So, or medium cases we can go with this. If it is very less turbulency, then you can go with 1%. Okay, I'm going to use it. So if you want in detail, you can use it this, where U dash is the root mean square of turbulent velocity fluctuating, and U is the mean velocity. So based upon the Reynolds number, so that I'm going to use it. So now we know that we have to use this medium cases, 1 or 5%. I'm going to use it, that is of 0.05. So I'm going to use it, right? So I'm going to use turbulent is 5% and dia is this. So temperature, how much temperature is it having? So in terms of Kelvin, now what they have given here, so they have given is 20 degrees. So that you mean, what do you mean by this 20 degrees? 20 plus 273.15, then how could be this? How much it is? Fast, what is the value I have to give? That is like 293.15 Kelvin. 20 plus 273.15. So that I'm going to use it. Just give okay. Yes, inlet we have defined. Then what could be the outlet? Outlet, pressure outlet, go with edit. Movement. So here I'll go with direction vector. Along in the which direction? Y direction, right? I'm going to use in the Y direction. Okay. So put it in the Y direction, which is having at the outlet, right? You can go with here normal to boundary. Yes, I'll go with here. So here I'll go now. This is, you can put it to 0, and this could be flow direction is 1.2 meter per second. So coordinate system we have components normal to boundary, no direction vector. We are giving only outlet, right? Outlet, inlet, large inlet. Sorry, no, sorry, this we are not going to give. Let it be 0. This is 1 unit, because we are giving this outlet, because the small inlet I have to define this. I was thinking about that. Yes, just put it to cancel. So what you do is go for here, inlet large we are given, no, inlet small, you can go small inlet, go with edit. So what you do is I'll go with here components. So that's in the Y direction, no, go for here. How much it is having? So which is having 1.2 meter per second, and intensity is, temperature 40 degrees, intensity 5%. So I'm going to give, so that is of 1.2 meter per second, and intensity and hydraulic dia. So intensity 5%, hydraulic dia is how much it was? That is of 25 mm. Okay, what is the temperature? So this is how much it was? 40 plus 273. 40 plus 273.15 Kelvin. So how much it could be? So that you can give is 313.15 Kelvin. I'm going to use at this, right? So no need of giving this outlet because it doesn't require outlet, right? So once we done, if you want to give, you can also define it. You can go with here. So intensity and hydraulic dia, which is, we know that hydraulic dia is 100 and intensity 5%, you can give it here, right? So that we are going to do. Again, you can save it, this project. You can save this, right? So once we done it, the boundary conditions, then dynamic mesh, already we done a good mesh. Reference values, I'm not going to take any reference values. And the other method is solution method. So this is very important, solutions. Now how you want to solve this problem? This is type of model you are using. Now this is the solution, how you want to solve. In the solution method, we are solving by simple method. There are 4 types: simple, simplex, PCO, coupled. So if you are mostly allocating for pressure type of problem, then you can go with PCO type of problem. Suppose you want to go with temperature and all, you can go with simplex. So I'll go with simple method, just general cases. See, sometimes it will get collapse, don't get worried. I'll open it again, just double click on this because already we saved, right? Not a problem because already we saved it. Automatically data will be restored. Better to use update versions so that it will, because I have license, but that's the reason I'm not changing this version, because if you have license, that won't be the problem. So already it is showing now. So you can cross check it. All the inputs have been given in the proper order or not. Yes, everything is fine. So no need of go with solution methods. So in the solution method, I will go with simple method. So temperature is important, no? You can go with the second order. What do you meaning of this first order, second order, sir? See, when you talk about elements, okay, when you talk about elements, so we know that this is one quad element and this is one tria element, right? And in terms of 3D, this is hexahedral and tetrahedral. Now quad element, this is 4 noded first order element, 3 noded first order element. Then how could be second order element? When you split this quad element into other quad element, like how, sir? Now when I split this quad into other, this is like second order element, you can call this. That means more precision you will be getting. 4 noded, that could be 4 plus 4. How much it will be? 8 noded element it will be become. Then how could be this? Again, this will be split into, in this cases. Then could be 3 plus 3. So that is of 6 noded element. Right? More area which is going to covered when you do know. When you keep on splitting, the more area it is going to covered and more precision you will be getting that. Right? So once we done it, so then what you do is, I'll go for temperature. I want to calculate more precision. No? Energy, yes, second order we have. Turbulency, you can put it here, second order also. Turbulency, you can also put it, turbulent kinetic energy you want to use it. I'll put it here, second order. Turbulent kinetic energy, this also I'm putting it to second order. Movement, which is okay. So once we done it, then go for solutions. I'm not going to use, because whatever the inputs you gave in the boundary condition, it is going to automatically, it is going to reflect here. Okay, so go with the monitors. Now what is your intention? No sir, I want to see the results over this outlet region. I want to see the results over this outer region. Sir, what sort of result you want to see? So create, what, at which location? You can go with the outlet, you can go with the name, so that it can easily identify. That too, at the outer region I want to plot it. Even I want to plot, even I want to write that file also. The write in the sense, it is going to save that file. So what sort of results you want to see? I want to see the temperature. Okay, so here you can change to, I'll go with here maximum, phase at maximum, I can go with that. So what variable you want to see? I want to see the temperature at which region? At the outlet region, right? I'll go with outlet region. So try to give okay. Yes. Now you have given temperature. No, sir. I want to see also no velocity. Also, I want to see. Again, I'll go with the velocity, like outlet velocity. You can give the name outlet velocity. You can give velocity. I want to see that. Even that also, I want to see the graph. I want to write that. You can give with phase at maximum. So what do you want to see? I'll go with here velocity at which region? At the outlet region also. Okay, I want to see that. I want to look at that region also. So once you given this, so this two important you are going to calculate, even though other important parameters also going to calculate, but mostly you are focusing on temperature as well as the velocity. So now go with solutions. What do you meaning of this solution initials? Whatever inputs you have assigned, that means you are assigning to the model. So try to initialize this. It is going to initialize.
Sir,
Yeah, please.
sir, we have CFD post, right, to view the results. But why we are using this monitor to view the temperature difference and pressure difference? So we can also view the results in the CFD post also.
Let me complete my answer. See, now I was good at Workbench, but I was not good at in the Fluent application. I was not good at this Fluent application. I was not good at this Fluent application. I was good at Workbench. No, sir, I was good at in the Fluent application. Whatever results I want to see in the Fluent, I can see here. No, sir, I was not good. I was not able to, no, I was not, I was new to this environment, but I was good at this Workbench environment. I want to see only results in the Workbench. Then you can do it. You want to see the results in the Fluent, then you can see it. Whatever it may be. Both are in same, no, both are Ansys itself.
Okay. Both results are same. So there is no nothing difference
both
between
are
this
same,
one.
both are. Because the thing is that environmental will be same. Environment will be same, results will be same, but the type of using will be different.
Okay.
Okay, you can just expand this. Now what I do is once we done it, go for run the calculations. So what do you meaning of this iterations? What do you meaning of this iteration? Now what happen is, now the fluid will flow. Now I'll go for some 300 iterations. I'll go with some usually I'll go with some 300 iteration. What do you meaning of this? Anyone? What do you meaning of this 300 iteration? If you know, okay, fine. Otherwise I'll going to help you.
Number of like
Yeah.
What do you
Sir,
mean?
after 300 iterations, it will converge.
No, it is not converge. See, I'm saying is I'll giving this 300 iteration. That means whatever inputs you are solving, it is going to solve 1, 2. First time it will going to solve. Second time again, with the inputs, whatever inputs you applied, first time it is going to solve it. Second time again it is going to solve. Up to 300 times it will go to solve it. Until you get a constant value, my solution will get converged. Suppose my solution I'm getting constant at some 50 iterations, it is getting constant. So then the problem will be solved. It is going to get converged at 50 iteration. It will shows us in the command. No, sir, if it's not getting converged, might be again we have to go with 200 iterations. If you got exact calculations, if you want exact calculations, then you have to keep on increasing iterations. No, sir, might be I cannot say that, sir, how much I have to use iteration. You cannot ask me that question because it might be take more than 300 or it might be less than 300. It is not depends upon us. No, if I give for 300, it might be solved around 50 to 60 iterations also it is going to solve. Until it get a constant input, the solution get converged. No, sir, if it is not getting converged, then you have to increase 200 iterations. I hope you understood this. Understood?
Yeah.
Okay, so that I'm going to use it here. Now I'm using 300 iterations. That means first time it will go with the same inputs it is going to apply. Second time it is going to apply. Third time, fourth time, until you get a constant values, it is going to keep on solving the problem. So once you get constant value, then it is going to problem will be get converged and it shows problem is been solved. It is converged so and so iteration. You can visualize the results. Now what I do is I'll try to calculate it. Now you see, so we have given x velocity while you can try to observe it. Okay, so this is your temperature. You can see, first iteration, second iteration, third iteration, up to 300 it will go. So until you get a straight graph, then it is going to stop that. So 9th iteration it is went, 10th iteration it is went, until 300 iteration is going to it is going to happen. So this is at the outlet, what template, or you can go with the velocity, how the velocity is having. Okay, so this is like temperature, and this is velocities and the total residuals, x velocity, y velocity, z velocity. You can give it even including with temperature also. You can see energy, k epsilon, k value, epsilon value, x velocity, y velocity. You can have all this. No, you can see this k epsilon value, the red color, I mean yellow color, which is indicating. Until you get a constant value, it is going to stop. I mean, it is going to solve the problem. Mostly some of the industry, they'll go with up to 1000, 2000 iterations also. Today, is there any person new to this session? Anurag, yesterday you were present. Kishore.
Yeah, sir. Today are present.
Yesterday you were present, Anurag.
No, sir. Yesterday was absent, sir. Today I'm present, sir.
Why? What happened? Why you were not present yesterday?
Actually, sir, on yesterday I was facing a fever, I think, so that I could not.
Yeah. For one day again the fever gone.
Sir,
the difference of one day, fever is gone.
Sir, I actually conditions not well. Actually, I'll came here, then I'll join in center, I think. So I don't want to come in center until I will not fit.
Okay.
Yeah, sir.
What
so
about Kishore? Yesterday you were joined?
Hello. Yes, sir. Yesterday I joined, sir.
Okay, I'm just seeing the new names. Even I know Ranjit. Ranjit Ram and Ranjit Ram. Both are same or what?
Yeah. Both are same, sir. I have some audio issues, so that is why I'm connecting on my mobile itself also.
Okay.
Hello, sir.
Yes, please.
Sir, Anurag is speaking, sir.
Yes,
Sir,
Anurag.
Sir, one doubt, sir.
Yes, Anurag, please go ahead.
How can identify rotation will be take 300 times?
You can see, right, iteration is showing 20, 40, 60, 200. It is it is showing the iterations, right?
Sir, any value can take, sir.
I didn't understood.
I'm telling, sir, now you took 300 times iteration, sir. So
Yes.
So, sir, can I take 200 time or 100 time?
You can take it, but if you're not getting converse, better to take more values. Might be if you're getting, might be to get converse at 200 also, that will be better, right? You give particular 500 iterations or 200 iterations, you give it. If it is solving below the 200 iterations, that is okay. But if it is not taking again to see, now it is get converged at this. At what 216 it is get converged.
Okay.
At 216 solution it is get converged. That is now it is showing the constant value. From here it is showing the constant value. Then it has been converged.
Okay, sir.
Now if you give 200 iterations, then what about the 16 iterations? Right? Yes. Better to give some more values. If you get less more values also, it might be wherever the solution get converged, it is going to solve that. It is going to stop there. right? So just go with OK. So go with graphics. Now in that graphics, you can go with counters, go with setup, counters, setup. What do you want to see? You can go with field, nodal values, global range, auto range. So what you want to see the results? So I want to see the results of temperature, or which I want to see the results of velocity. For example, I want to see the velocity. Which region? At the middle region, right? Symmetry is your middle, right? So symmetry region, try to display that. So change, if it is not displaying, then change type to here convergent or no counters of velocity magnitude. You can see. Just try to fit to the screen. You see how the velocity has been changing. This is your velocity. No sir, I want to see the temperature. Okay, you can go with the temperature also. So change type to temperature, go with display that how we have temperature, right? So max one is 313 point. No, you have this. No sir, I was the both values are same. 31 the temperature you can see 313. Maximum is over here. So minimum you have over here, right? So I'll be showing this. Okay. So what you do is you can save this project. Now I want to see at the post process. So in the workbench, I want to see that both results will be same, but more visualization will be there in the post process. Expand, just double click on this results, CFD post process. Even here also you have dat file, .dat file. You can see I've been saved here in the Fluent, right? In the Fluent, when you expand this, you have dat file. Flow mix. You can see output file, no .dat file. This is like setup file. You can go with this directly. If you want to share this file to somewhere, you have to share this output file, .dat file. This is very, very important. You can see how much MB it was there. The results will be saved here. Okay, and the post process. We have not done any post process, right? The post it is going to save the animation and all that stuff. It is going to. So just put it here, normal view. So like which plane? I'll be enabling this middle plane, symmetry plane. I'm going to enable. Now what you want to see the results? Now I want to see the results of different results I want to see. So first I'll go with the velocity. So what you do is go for counters. So I'll change name, put it names to velocity. Okay. Just give it okay. Now at which region? Start from which region? Location is start from inlet region, no? Or inlet at the symmetry region. So what variable? Pressure variable. You can see that. This is your pressure variable. How much we have? So you want to you want to change this legend pressure how you have, right? So you can see it. Domain is fluid. You can take it here. You can go with solid, or you can go with all domains. You can take how we have the velocity. Okay, so maximum how much it was having, pressure which is having, showing a minimum maximum, right? Velocity at the symmetry region. So what you do is velocity variable, what you have, pressure it's showing. I'll go with the velocity. So how we have the velocity, so which is having 1.3. You can see minimum is 0, maximum is 136 we have. No sir, I want to see for you can go with the probe, click out on this probe. You can change, put it to velocity. You can put it here, then you can click it on the particular area how much we have. So that area how much it is having at the probe of location 0.0, how much velocity which is having 3.8 over this area 3.8. I mean velocity is 0.4. So this is X location, Y location and Z location. X, Y probe at X location, Y location. Automatically it is indicating that. Now here what is the velocity which is having 0.6 meter per second. Over here how much it is having 1.2 max here, right? We gave 1.2 we have. So what is the velocity at the outlet? What is the velocity? 0.5. Then what could be the temperature, sir? So put it to again, you can undo this velocity. So go for again counters. You can put it temp. You can give any name for your identification. Temp. So which region? At the inlet region you can go with small inlet. Small inlet. So what variable? I'll go with the temperature variable. Try to do that. So I think here it is showing or what. So at which region, all domains, temperature at symmetry region, you can go with that. This is at symmetry region, right? 313 we have. Now this is velocity. I'll undo this velocity at symmetry region we have. Now what I want to see is I want to show you the other inputs. I'll go with here steam lines. So this is a large inlet. Okay, large inlet. So which region, starting from inlet large, okay, velocity. So try to apply it. This is like steam lines. Again you can go with again steam lines. So you can go with small inlet. You can go with a small inlet. So starting from small inlet, you can go with that small inlet. So try to apply it. So both you have, right? Just try to fit to the screen. Now you can just generate animation, how the fluid is moving. I mean, you can go with here the animation. So both large and small. So you can just change this slow mode options. So how you want to see the symbols, ball. I'm just decreasing this ball size. You can put it here less size. Just try to play it here. I think what happened, just stop it. Okay, how it is, only this small inlet it is passing. So what I do is I'll stop it here because we selected only one. Okay, so again you can go with this. You select both of them. You can see this. Okay, so this way you have to do it. Once we're done, you can save this. You can save this. Just expand this. Save to movie. Just go with here. So where you want to save it, it is saving in the desktop. You can put it here. It is saving the downloads. Let it be this. Let it save in the documents. CFD. Like where you want to save it. I want to save it in the Fluent. You can save it this. Okay. Just it is going to save it there. So now that means it is saving the file. So now what you are going to do is, before we saved it, so you have to change this dia. So instead of 25 mm, you have to change this dia to 19 mm. A small dia to 19 mm. Now you have to observe what changes you've been done. Change here, it was 25 mm dia, right? So change dia to 19 mm and see what is the temperature, what is the velocity. Now we observed that velocity is 1.6. We have it here. We have 1.6. We have the velocity. I mean 1.6 we have. Just try to stop it here. Might be it is going to save it. Definitely is going to save it. We'll have this. You can have this. Give more frame rates so that you will have fine. So velocity we have 1.3. No, you see the change. Change dia to 19 mm and let me know what changes we have to do. Understood? Change this small dia to 19 mm.
Yes, sir.
And try to calculate the result with same inputs.
Okay, sir.
And please do submit it. Okay, so I'm sharing my the mail ID tech support .cae2
Sir, can we have the hands-on files and the PPT, sir?
Yes, just give your mail IDs here. Tech support dot. You have to send to this mail ID.
Yeah. Sure. Thank you.
Okay, so please do send it, and yeah, I'll stop the session here. We can move with the other topic.